Alright, so the last two problems on this problem set are more proof-based. So let's go ahead and do these. So 16. Let x and y be the random variables that count the number of heads and the number of tails that come up when two fair coins are flipped. Show that x and y are not independent. Okay, so we're trying to show, according to our the definition that we saw, this case, e of x times expectation of y is not going to equal to e of xy. So I guess let's figure out all of these values separately. So first, let's go and find e of x. Alright, so e of x is going to be, we are seeing, well, we're going to have to count. So let's do when n is 0. So number of tails that come up when two fair coins are flipped. So this is going to be 0 times, well, the number of just a 0 tails, that's going to be head. Okay, so this is n. The number of, well, this case is only going to be 1 over 4. Okay, and then add that to the case where I guess now n is 1. So we have 1 tail. So we have 2 cases in that case. It's going to be either head tail or tail head. So this would be times 2 over 4. Plus, I guess our number n is 2 now. So what's the case? What's the probability of having 2 tails? So there's only 1 case. That's tail. So that's going to be 1 over 4. So if we do this, this is going to end up being 1. So the expected value of x, the number of heads, is 1 for 2 fair coins. And likewise, expected value of y is also going to be 1. Alright, so far we have found e of x, which is 1, and also e of y, which is also 1. So let's go ahead and find this one, e of xy. We're going to have quite a bit of cases for calculating this. So the first case is when x is 2 and y is 0. So what's the case where we're going to have 2 tails and 0? This is just going to be 1 over 4. The only difference is x times y. This is going to be 0 because we have 2 times 0. The second case is x is 1 and y is also 1. So what's the probability that this is happening? It's the same case here. We're going to have 2 over 4. We're going to have either head tail or tail head. And the thing that's different from the previous calculation of e of x and e of y separately is that x times y is now going to be 1. We have the last case. This could be when x is 0 and y is 2. So again, the probability for this, as we have seen, is going to be the same as 1/4, and x times y is going to be 0. So e of xy, this is going to be 0, just the number here, times 1 over 4, plus 1 times 2 over 4, plus 0 times 1 over 4. And that's going to give us 2 over 4, which reduces down to 1/2. So therefore, we have shown that because 1 times 1 is not equal to 1/2, we can conclude that that is true, and thus we have shown that x and y are not independent. Alright, and this is the last question. Let x be the number of appearing on the first die when 2 fair dice are rolled, and let y be the sum of the numbers appearing on those 2 dice. show that they're not independent. Okay, so this is pretty similar to the previous problem. You guys can either calculate the actual numbers and the expected values and the probability. But since I've already shown you how to do that in the previous problem, I'm going to go ahead and take another way of showing and solving this problem. So I'm going to solve this by, or prove this using the linearity expectation. Okay. So let me start with e of x, y. And we know this from our textbook that this is going to be x times x plus w, where w is, so I'm saying x plus w is our case of y. And this is going to equal to, just from the distribution rule, x squared plus xw. One of the definitions in the properties of expectation is that can be extracted. So we have x squared plus expectation of xw. All right, and now here's the important part. I'm going to say that this is greater than the expected value of x squared plus e of xw. And this would be the case, and well, here I'm using the fact that e of x squared is greater than e of x squared, and this is because x has a non-zero variance. So I guess this is kind of our first problem that we are encountering with the idea of variance, which you have read in the textbook. Okay, and so again, so I'm going to use this now. This is the same thing as e of x times e of w, and that gets us to e of x times e of x plus w, kind of the other way of that we did this from here to the second line, and that is e of x plus e of y. So there we go, we have just proved that e expectation of x times y is actually the sum of those two, not the multiplication of those. This is just one way. I used lots of definitions, probably the most classical mathematical way of showing. But again, for your homework, if you would like to just actually go ahead and count the possibilities and using the probability to do that, that might be a little more visual and discrete. So you guys can go ahead and do that for this problem.